This is a presentation of cross-flow heat exchangers, section 10.3 by the STUDious Masters. The term cross-flow means that the fluids flow at right angles to each other as they pass through the exchanger. Some examples are automotive radiators, condensers and evaporators, oil coolers, and heaters. These may look similar to a CPU heatsink, but these are designed to transfer heat from one fluid to another and not from the metal structure to a fluid. An example can be a vehicle radiator. It is a common mixed-unmixed cross-flow heat exchanger, where the coolant is unmixed and the air is mixed.
Figure 10.6 shows examples of a cross-flow heat exchangers that contain mixed and unmixed flow passageways. Figure 10.6a shows a mixed-unmixed system, and figure 10.6b shows an unmixed heat exchanger. Figure 10.7 shows an unmixed cross-flow heat exchanger in which the metal used are made into the shape reminiscent of a sine wave. This type is primarily used in some oil coolers. Figure 10.8 shows a finned tube type of a design in which tubes are pressed through thin metal fins. The fins act to increase the heat transfer due to the increase in surface area. In order to define Nusselt's number, we first have to begin with the Colburn modulus, which is defined as the heat transfer times Prandtl's number to the 2/3 power divided by the mass flux defined as density times volume and heat capacity. Once we derive that, Nusselt's number is approximately 0.178 times the Reynolds number to the 0.59 power times Prandtl's number to the 1/3 power, which is equation 10.19.
The primary objective in heat exchanger design is to achieve a system that transfers heat at minimum cost and within a minimum space. So the following are the examples of the applications of heat exchanger in the industry. So based on the direction of the fluid flow, heat exchangers could be classified as parallel or cross-flow heat exchanger.
The term cross-flow denotes that the fluid flow at the right angle to each other. As the fluid flow through the exchanger, they could be either be mixed or unmixed.
So these are the different variations of the mixed and unmixed counterflow design. So the first one is mixed, unmixed, and the other one is unmixed and unmixed. So the next one is a little bit different from the previous one because it has a sine wave cross-sectional area. And the last one is a fin tube design, which ensures a maximum surface area in order to provide a larger number of transfer units for heat exchanger.
The heat transfer data for cross-flow heat exchanger is expressed in terms of a parameter called Colburn modulus, which is a function of the Prandtl number and the mass flux. It allows for finding the convection coefficient for the S side of the heat exchanger. The S side heat exchanger coefficient is, however, usually much smaller than that for the liquid side, and as much, the contribution of the liquid coefficient for the overall heat exchanger transfer coefficient is negligible.
So the effectiveness of the heat exchanger is a function of the capacitance of the cold side and the hot side. So the ratio, based on the ratio of the capacitance of the cold side to the hot side, we use the following equations. If the ratio is less than 1, we use the first set of equation. Otherwise, we use the second set of equation. And based on that, this is a variation of the effectiveness with the number of transfer units. For the first configuration that we have on the screen, it's for mixed and unmixed. But we're using the fluid with minimum capacitance as mixed. So the second one is the same thing as the previous one. In this case, we're using the fluid with minimum capacitance as unmixed. Now the last one, we're using mixed and unmixed.
Now we will go over the suggested order of calculations for analysis of cross-flow heat exchangers. First, you need the complete problem statement, followed by potential heat losses or other sources of difficulties. Then you need two assumptions. The first is steady state conditions exist. The second is fluid properties remain constant and are evaluated at a specific temperature. You need to decide what temperature this is. Then you need to define what your letters and numbers represent. An example of this is number 3. W as a subscript refers to the warmer fluid. The first step of solving this problem, part A, is finding the fluid properties. These can be given to you, looked up online, or looked up in the textbook from tables. You need to do this for both the warm fluid and the cold fluid. Part B is the heat balance. You can find the heat transfer for both the warm and the cold fluids here. Part C is finding the log mean temperature difference using the counterflow formula. Part D is to find the correction factor if needed. The correction factor is a function of the capacitance ratio R and the temperature factor S. Once you find S and R, you can look at figure 10.11 for a mixed unmixed or figure 10.12 for unmixed unmixed to find the correction factor needed. Part E is to find the UA product. That is equal to Q over F times the log mean temperature difference.
Next, in the suggested order for analysis, the capacitance of the heat exchanger is calculated. The flow through the heat exchanger must be determined to be mixed, unmixed, or unmixed, unmixed. The overall capacitance for the mixed, unmixed is a ratio of mixed capacitance over unmixed capacitance. The overall capacitance for unmixed, unmixed is a ratio of the smaller individual capacitance over the greater individual capacitance. The NTU method is used to calculate the rate of heat transfer in heat exchangers when there is not enough information to calculate the log mean temperature difference. Here, N equals the UA product from part E divided by the smaller individual capacitance. The effectiveness is determined using the overall capacitance and the number of transfer units. With these two variables, the effectiveness E can be found with figure 10.13 for mixed unmixed and figure 10.14 for unmixed unmixed. Here are figures 10.13 and 10.14. To determine outlet temperatures, first compare the individual capacitances of the warm and cold fluids. Depending on which is greater, use the equations here along with calculated overall capacitance and effectiveness to determine corresponding outlet temperatures. Using flow rate along with tube and duct diameters, the velocities of the warm and cold fluids within the heat exchanger can be determined. For pressure drop calculations, in cross-flow heat exchangers, a minor loss coefficient of 10 is used. The pressure drop for both fluids is equal to the minor loss coefficient times density times velocity squared divided by 2. The frontal area required can be determined using the UA product in unison with figure 10.15 shown below. At this stage, all variables and values necessary for the analysis of cross-flow heat exchangers are known, and pertinent and relevant information requested by the problem statement should be stated and presented.
Example problem 10.2 reads, a cross-flow heat exchanger is used to cool water at the test stand of a diesel engine. The water enters the exchanger at 93.3 degrees Celsius. Air in the room is used as a cooling fluid. The fan available can move air at 0.315 grams per second. The frontal area of the heat exchanger is 0.186 meters squared. If the flow rate of the water is 0.088 grams per second, determine the expected outlet temperatures of both fluids. Before beginning the problem, it's important to state some assumptions. For example, number 1, steady state conditions exist. Number 2, fluid properties remain constant and are evaluated at average temperatures for each fluid. In Part A, fluid properties were collected for water at 84.5 degrees Celsius and air at 34.4 degrees Celsius. Part B is where capacitance was calculated. As you can see, the minimum capacitance came from air and maximum capacitance came from water. In Part C, Table 10.15 from the textbook comes in handy for the UA product. That is important for Part D, where number of transfer units is being calculated. In Part D, N equals UA divided by minimum capacitance, which was found earlier, which equals 1.665. Using number of transfer units and capacitance, Part E is calculated, which is effectiveness. Effectiveness is used to calculate Part F, which is the outlet temperatures. The outlet temperature of water is 62.8 degrees Celsius, and the outlet temperature of air is 56.7 degrees Celsius. Part G calculates log mean temperature difference, which is 39.06 degrees Celsius, counterflow. In summary, the question asked, determine the expected outlet temperatures of both fluids. In Part K, we have summarized the information requested. Water T2 equals 62.8 degrees Celsius and air T2 equals 56.7 degrees Celsius.